I'm audible.
Yeah, good morning, dear participants. Sorry for the 10-12 minutes delay, but it was having a few issues, and even at Dr. Sandeep's place, there was few issues. Fine, so it got rectified now. So welcome to the fifth day of session on design of experiments in engineering ACT sponsored STTP program. And today we have a resource person, the Dr. M. Sandeep Kumar. And like those who are new, let me quickly introduce him. He is a faculty of BVRIT Raju Institute of Technology, associate professor. And he has PhD from NIT Warangal, MTech from NIT Calicut, and BE from Maharashtra College of Engineering. His fields of specialization include nanotechnology, machining, eco-friendly cutting, and manufacturing technology. And he has published nearly 17 different journals and one patent. And he has also received the Best Paper Award. And in this sessions, he has already covered the hands-on walkthrough design of experiments and also factorial design of experiments. And today he's going to take up a very important topic that is about response surface methodology, which I hope many of you have already heard of it and would like to introduce in this RSM in their experimental study for their publications and their thesis work. So I request Dr. Sandeep to take the session. Over to Sandeep, please.
Thank you, Varun.
Right.
Yeah.
Okay.
Thank you, Varun, Dr. Varun, for giving me this opportunity. As dear participants, a very good morning. I had some professional, or you can call personal commitments, not professional. So I couldn't make it on time. Sorry for the delay. Yeah, so around 8 members are there. So I will be starting the session. I hope the other participants join, and I request the coordinator to once again post in the group, STTP group, if someone is unaware or someone just logged off.
Yes, sir, I'll do.
Yeah, please. Yeah, so we'll wait for 2 more minutes because the starting itself is important for us. So we'll wait for 2 more minutes and we can start the session. Okay. Will it be okay, Varun?
Yes, no problem. 2 minutes is fine.
Yeah, 2 minutes we'll wait, and at the same time, if you can post in the group. Yeah.
So in the meantime, if any of the participants would like to interact with us, it will be great, because very few instances where we could have interaction. So you could take this time to get to know, or if in specific you expected something and if it is not meeting those requirements, also we can try to address it at least now or in the next coming STTPs. Like you already know that this is a sequel which we are supposed to conduct under the ACT STTP sponsor. So if any participants would like to share their experiences, views, of course it's not a feedback, but I just want to know within the given short time if anything is there that we can provide you with.
Yeah, so dear participants, this whole STTP which was planned and written was like for seeing that or keeping in mind the beginners or the researchers who have just started their thing and they are stuck up with all this what you call barricades. Okay, we can call it as barricades also, because it's actually a very tedious process, and most of us just we drop our hands because of this thing, and it takes a huge lot of time for and consuming. It's a huge time consuming process. So this is actually the easiest way, and that is what we would like to. And the previous session was very interactive actually for us, and many of the researchers from Anna University and others were there who just interacted and got their doubts cleared up. So if anyone is interested, and don't hesitate or have any language barrier. So please, if you have anything such kind, we can just try to see that we solve your issues.
Unmute themselves is available, so you can unmute and you can speak. All right. Okay, Dr. Sandeep sir, you may start the session now. It's already 10:20 about to. So
yeah, is my PPT visible, sir?
Yeah, you can make it full screen.
Yeah, I'll do it. And my video?
Video, yes.
Okay, fine. Thank you. Yeah, so once again, I welcome all the participants on board to this STTP program and for this session where I'll be dealing with response surface methodology. Yes, it is a very fancy topic. Everyone is fascinated about RSM, and everyone wants to use RSM, and these all things are there. But yeah, let us see how good it is RSM. How good is RSM for our work, and till where we can, till what extent can we use RSM? So that is the whole idea of today's session. Yeah. So please let us continue with this. Yeah. So as everyone knows, response surface methodology is an approach in which experimental techniques invented to find the optimal response. So we try to see that we get some optimal response of this thing. So usually we try to see, yes, we do experimentation to see that we get some optimal conditions on which the output can be reliable on, and the regression equation. Yes, the regression equation also we speak about much when it comes to RSM. So regression equation is also a very important aspect or the thing which we are considering. Apart from that, we know that we get optimal responses. Yes, with what? Within the specified range of the factors. Okay, so that is also one condition. The regression equation, what we get is good, or it will act good within the specified limits or the ranges of the factors. So that is one condition where RSM is there. Okay. Next, the design are capable of fitting a second order predictable or prediction equation for the response. Okay, so whenever you go with a full factorial or a Taguchi approach, you won't get a second order equation. So the reliability on that equation which you get from the previous things was not that reliable, and this RSM gives or does study with the second order equations. So the reliability of the equation is good when it comes to RSM. Okay. Apart from that, when it comes to the quadratic terms in this equation model the curvature. Yes, so we are almost fascinated about curvatures, what we get in the true response function. So that is where RSM is aesthetically also you can say RSM is much more fascinated when it comes to representation of the results. Okay, representing the results with related to the responses and the input factors. So that is why RSM is becoming much famous nowadays. And apart from that, as the equation is of a second order degree polynomial equations, so understanding of this thing is much more important as an thing. And why I am insisting on this is like 2 weeks before I met a researcher who is pursuing his PhD and they wanted to know about RSM and all these things, and they some way they got an input that RSM gives very good results and all this, so I'll be using RSM. But indeed, is there any need for RSM? Okay, so that we have to check up actually. Apart from that, not only RSM, is there a need for full factorial or partial factorial or Taguchi methods or RSM? This all things have to be actually considered. Simply like because what I heard of from the researcher was like, no sir, just I wanted to use this and I wanted to just conduct experiments and I wanted to get some optimal value, so I used RSM. Yes, RSM is good, but we should know actually is it fit for us. So usually what happens is when this kind of condition comes up, what you do is you try to force fit the design and you try to conduct the speaking. Actually, it's not useful. Sometimes conducting the experiment. So the whole idea of this, or summing up the sessions what I have taken previously with this is the same thing. So you should be the participants and the researchers and the research community. Thus, it's a small effort from our end to see that what is to communicate actually what is the exact procedure or what is actually the exact step-by-step approach for getting this getting the optimum conditions. Okay, so with this, let us start. Yeah. So before getting into this, yes, everyone assumes why all these things are required, why RSM and all these things are required. So with a small example, I would like to communicate everyone with this. Okay. Yeah. So India, everyone is, I hope everyone is known to writing letters. And when we write a letter or an address, like nowadays, before we used to do on England letters or postcards or some like greeting cards, we used to write the address and post it to some and from address we would be having, right? So nowadays we use it for getting couriers or like parcels online. Okay, so yeah. So with that, let us see this address. So usually we write the address in this form. Yes, you are an Indian. You are good at doing it. Just suppose you are a foreigner or some person who doesn't know about the address. Okay. So usually how we start reading an address? Is it that a house number, street number, or a colony? I'll write this as colony. Colony and area, city, this is state and country. So if this is the case, how would I search this address usually? If I am completely new to a particular, let us take we are from some other country, and how would I actually, this is address, and I would like to search this particular house. Actually, it is a home address, right? So I would like to search a particular home address. How would I do it? Should I start from here, or should I start from here? So usually it is bottom down approach, isn't it? Top down approach. Sorry, not bottom up approach. It's top down approach. So how will I do this? The top means biggest area. I take the biggest search area. Okay. I take the biggest search area. First, I'll identify the biggest search area. What is the biggest search area first? Is the country. Okay. So in this way, biggest search area is country. After that, if I narrow down, it goes to Telangana. Then there is the state. Then which city I am searching for. Once I know the city, I'll search for the area for what I'm looking at. Once I get into the area, I'll go with the colony. In this colony, again, you'll be having some street numbers or you'll be having some house numbers, which will consist of some levels and factors. Okay. Some streets can be the levels and the door numbers and all this can be some streets can be the factors and the door numbers can be the levels. Okay. So what I am doing here is, what I am trying to do is, this person who is there, some X person, he doesn't know this address. So he has to use some top down approach, because I don't know actually how it is going on. Okay. Now I need to identify the area in which this particular house belongs. Then I'm narrowing down. Still further I am narrowing it down and this way. So what is the goal? The goal is reaching or finding an optimal address or an exact address. So usually we need an exact address. We don't need an optimal address. Optimal address means there'll be 4 or 5 houses and I'll be getting this address. No, I don't want that. Exactly in this case, we need an exact address. I don't want to by chance also get into some other fellow's house. Okay. So yes, in real term, we do all these exercises. This is just one such example where you are trying to see that I want to get into some or the other, I want to find one address. Okay. There are many such examples. Okay. So let us take this first example, what you basically do with this thing. Okay. Fine. So a person now he starts thinking, now I need to reach an person's home. Let it be your friend. This X person wants to reach his friend's home, that is some Y person's home. Okay. So that address was given to him. How will I do it? What this? Yes, it may be a childish for means it may be a cartoonist thing for representing this thing, but I hope that you can understand and map it to the real terminologies, right? Real life situations. So now the first address was like I would from the world map if I can go, or you can see how the Google operates also. Okay, the Google also operates the same with the same step-by-step approach. Okay, so now the first approach was the country. Okay, so now yes, with this what I did is I bottomed down some areas, and what I did is I got this country which is named as India. Okay, so once this thing is done, the next step I'm going top-down approach, right? So first was the country. I got down to the country. So once I have identified the country or the area in which I need to search, this is the area of search. Okay, this is called as area of search. This is called as area of search. This is called the broad area of search. Okay, so with this can I find my house in this? If I have an India map on with me, can I find my house, some 5 person's house in that? No, I can't do that. So what I have to do is I am further narrowing down my search, isn't it? Search area or area of search, what I am doing is I am further narrowing down. So instead of country, I am going for state. Okay. So this is the state. So now what I am doing here is, just 1 second, guys. Yeah, please. So now what I did is, yes, first was a broad area where I wanted to search. Okay, this was my broad area and I started searching here. Now, anyhow, I couldn't find it. So what I'm doing is, I'm now narrowing down my area, search area. I'm going with the state now. So once I go with the state, how much I am narrowing down the area? Okay, now it is just a state. Okay, so in this state, what I have to do is I have to find my city anyhow, because with this again, if I have a state map there, I can't find the thing what I am searching for. Okay, I am searching for some optimal address. Okay, optimal house or optimal address you can say. But when I go with state, there also I can't find it, isn't it? So what happens is with the state, now I'll go for city. In this state, I'll go for city. I'll go for search for city. Where is this city? Yes, this is the city. Okay. Yes, sorry for the inconvenience if anyone is from other state. Yes, some of them are from other states. So sorry for the inconvenience. But yes, this resembles the same thing. Yes. So now this is the city which I narrowed down. So the search area from the Indian map, now it is narrowed down to the state. From the state, it is narrowed down to the city. Now I know that the address what I am searching for, or the condition what I am searching for, is in this area. But yes, still Hyderabad, if you see, the radius of Hyderabad itself is 50 kilometers. Okay, if I take a center point from here and draw this, it is 50 kilometers. The radius itself is 50 kilometers. Okay, so you can assume, and now if I rotate this 360 degrees, where will I find a small house? Okay, this is just a small house, and this radius itself is 50 kilometers. So you can assume like a length and breadth. Length and breadth, if I search also, it is very difficult for me. So now what I'll do is, instead of city, I'll go to area. Okay, so now what I did is, I narrowed down to one area. Okay, now I narrowed down to one area. Now I know that at any cost in this narrowed, actually I couldn't fit one more, that is colony also. Colony. From area, then I narrowed down to colony. Okay, so now anyhow I know that whatever I am doing is in this colony. My search or the optimal condition, what I am looking for is in this colony. Okay, yes, what is the difference is I need to search the streets, in that streets, that particular thing where the optimal addresses fit. Okay, so this is the colony. So once I know where is the colony, is it very difficult for me to search this address? House number, street number and house number. Search in this particular colony. If I'm directly placed in this colony, it is very easy for me to search the area, and I'll directly say that yes, this is the optimal address. Okay. Yes. But now let us come back again. Am I directly knowing this condition? Yes. Am I knowing directly this condition where the house is directly fitted into, or where the optimal conditions are lying? Or if I say this area, okay, do I know exactly in this area, or what is this area in which the optimal conditions actually are available? No. When it comes to practically speaking, no researchers know it exactly where, in which what you can say is narrowed down area I have to concentrate so that I will get optimal condition. Okay, so this narrowed down area, what I call it as, okay, maybe the area or the colony, I call it as RSM. Okay, response surface methodology works very beautifully when you know that in which you are very certain, or you can say that you are very certain that the area of search, what you constrained the area of search is exact. Okay, so you have selected an area of search, or you have narrowed down to an area of search, and you know that it's exactly what I am in that area, exactly I will get the optimal condition. Okay, so can any researcher guarantee this, that in this exact area of search I have got it? Yes, you may be knowing from the literature survey and all these things, you may be knowing everything. Yes, people have done experimentation here and people have done experimentation there and all these areas. Okay, so is there any way, or yes, from the experimentation, if you have all the conditions, like if fortunately you have received a journal paper or a manuscript in which the experimental conditions are exactly with what you are working on, then yes, then with the same materials and same set of conditions or the parameters, yes, then naturally, yes, you have narrowed down to this area and you are looking for an optimal condition in that area. That is okay. But generally what happens when a new researcher is starting his work, it will be like this. You will be like an Indian map. You don't know actually where what you are looking for. Okay, so that is why I name it as one factor at a time. Okay, just for namesake, I am saying this. We can name it as an one factor at a time. Okay, it's not exactly that, because one factor at a time actually looks for levels. But as far as search or the flow chart or the condition is there, we call it as one factor. I named it as one factor at a time. So usually what happens with this is I am narrowing down. Actually, one factor at a time combined with 2 to the power of k full factorial. Okay, so when you do both of this is for levels and this is for factors. Okay, So when you conduct one factor at a time, you know the levels at which you need to fix the experimentation. And when you go with 2 to the power of k full factorials, you know the factors which you can narrow it down. So once I know both of this, then I can go with a full factorial thing. Okay, full factorial experiment I can do, which gives us the results with all the combinations and all that. But still, this full factorial is actually a broader area of search. Full factorial is still a broader area of search where you try to search all the length and breadth. Okay. So if I want to search this address in Hyderabad, what I have to do is I have to search through the length and breadth of this Hyderabad. Okay. Length and breadth of this Hyderabad. So it is a 3 to the power of k full factorial. You can take n number of factors, goes on increasing. Okay. 3 levels and all this. So what happens is with this, I will get the complete map of this Hyderabad when I do full factorial experiment. Okay. So when I do full factorial experiment, I will get the complete map of this Hyderabad. So I will be knowing in and out of this Hyderabad. Okay. Of the city, in and out of the city. So wherever I want to know, whatever the condition is, whatever is for the response, I will completely know actually. Okay. In any area, like any area of search, whatever I want to know, everything I'll be knowing it. But is that actually the thing what I'm looking for? No. What I am looking for is some part. I am looking only for some area in Hyderabad. Okay. That area is the colony or the, you can call it area like Chengichal, I have written it for namesake. So this is the area what I want to concentrate on. So if I concentrate on this area, a smaller area, this gives us a broader picture actually. FFD, that is full factorial design, gives us a broader picture basically. And when I go with this one, okay, yes, I'll get a broader picture and I'll get an equation that is actually for a first degree polynomial equation, I'll be getting it. That is okay. But I want to I want to assure that whatever equation I get it, okay, is it reliable and I can go for optimization using that equation and all that. Then I have to narrow down my search to a colony or an area. And here I should conduct the experiments. Okay, so here when I conduct the experiments, the equation what I get will be much more reliable, and the search what I am doing is much more optimal. So I will be getting a very good equation. And apart from that, what I am doing with RSM, the number of experiments what I am doing is actually I am reducing the number of experiments. In FFD, full factorial design, the number of experiments are more because I am going with all the combinations. I am going through the length and breadth. Okay, so once I narrow down the area, the number of experiments required for getting to that particular address is very easy for me. So what I do is here, the number of search what I do is very less. Okay, the search what I do, the number of runs or number of experiments what I do is very less, because if I have narrowed down to this level, okay, if I narrowed down the conditions or the factors or the levels to this level, then just I have to go to some of the streets, or if the signboards are there in that streets, I just have to just check it up, and directly, as I know the street number and the house number, I can directly get to the target, and then we can achieve success. Okay, so this is what the whole idea behind RSM. Okay, so let us start now. So an easy way to estimate a first degree polynomial model is to use a full factorial or a fractional factorial experiment. So the easiest way, as I was looking up, the easiest way to do is do it a full factorial design. But how many of us do it actually? You don't need a full factorial design. You just from 2 to the power of k, once you narrow down to the factors and the one factorial and the levels, you can directly go to RSM. Instead of doing the full factorial also, once you know the factors and the levels, you can directly narrow it down to RSM. Okay. Instead of doing all this, instead of fielding the complete area, you can directly narrow it down to RSM. But yes, ultimately, if you have, if you want to just go to the length and breadth of this and know the complete area, so there are some experimentation where you have to go through complete length and breadth of this. I don't want an equation. I don't want a beautiful equation, and I don't want to a second degree polynomial. That I don't want actually. Okay, this is just for aesthetic purpose or the equation purpose or the optimization purpose. So if your purpose is optimization or getting some beautiful graphs and relying on that area, or if you are, as I told you, if you have the data or if you exactly narrow it down to this data, yes, from the 2 power of k, you can get the factors and year levels and directly you can go for RSM. That is one way of looking into it. No, I got these levels and factors initially. No, but my requirement is to know actually how the complete area of search, because my experimentation cost is less and the time consumed for the experimentation is less, then why should I go for RSM? I'll go with full factorial design. I am not interested in optimization, but what I'm interested in is the complete area, search in the complete area or the complete domain. Okay, if I'm doing some survey, okay, if I'm doing some survey, exactly if I can, I wanted to give some examples. If I'm doing some survey, okay, if I'm doing some survey this particular area, how this thing is happening or what is this particular area, this people, or if I say I'm from a marketing background or NBA background, I'll be not interested in a particular area. Okay, I want a broader search area. Okay, what is the mindset of that particular people in that area if I want to search? Okay, if I'm like if you see I am from some retailer who wants to distribute, or I am from food industry who wants to distribute my food or who wants to sell my food in particular area. I need to know what kind of what is the requirement basically. Okay, so what I do is I'll conduct a search for the complete area now. For the city, I'll be conducting a search, and then I'll be knowing that no, this particular area is some X area is interested into this kind of food. And if I say I'll be entering this area, then this particular area is interested in this kind of food. Okay, this may be interested in some traditional food. This area may be interested in some fast foods. This area, so I can name it as Z, are a mixture of both this. Okay. So if I want to do this survey, then RSM wouldn't work for me. Okay, then I have to go for full factorial design. I will be searching the complete domain. Okay, Hyderabad is my complete domain, so I will be searching in Hyderabad domain and seeing that what is the mindset of that particular people. Okay, what is the mindset of the particular people, and then I'll be doing experimentation in that area or going for a survey in that area, and finally I'll be getting all the data. So what I'll be looking into response in the response way is, when I go with response, you can go with any number of responses. Okay, so if I take X response, Y response, and Z response, one is fast food, one is a traditional food, and third one is a hybrid, right? A mixture of Z is the mixture of both traditional and hybrid, where if you say there are people who are residing in these areas and neither from MNCs or neither from a village oriented thing. Okay, so in this area people like to have both the foods. Okay, so if this kind of example is there, I don't need to go with RSM. What I'll be doing is I'll be only searching, I'll be conducting experiments. Yes, the survey will be for every level and every factor, but if I want for X, I'll be knowing which area is optimal for me. So I'll be only distributing more in that area for this traditional food. Then if I have Y, for this Y, what I'll be doing is for the conditions will be same, but there I'll be getting an area which they'll be saying is very good for fast foods. They'll be using, most of the people will be interested in fast foods, and then the same area will give me Z. So what happens is with this search, I will be getting an area, and finally I know where I have to search. So this is one way of looking into full factorial design. Apart from that, if you go with some chemical industries or chemical or pharmaceutical things, where I want to know the combination of each and everything, right? Chemical, right? Even milligrams, they just add it in milligrams, and they want to know what is the reaction, the final on the response. How is it reacting on the final response? So yes, this can be done. When you have a broad area, you don't need to narrow it down to RSM. Yes, only typically, like when it comes to manufacturing, or the cost of the product is very high, and you want to get some beautiful graphs, and you want to go for optimization instead of conducting all the experiments. I want to go for optimization. Then yes, you can go for RSM. So I hope I have gone with the length and breadth of RSM, and let us go with now with RSM. How does it actually do. Yeah. So the same thinking search, narrowing down the area comes up. So region where actually full factorial search is done is the current setting. So if you want some improvement in that, what you can do is you can go for optimum or a region for RSM design search. So it is just an information to each and every participants here. Don't force fit the designs actually. That is what our Guruji Danesh sir from NIT Calicut used to always tell us actually. Right? Don't force fit. Just try to see what is your requirement. Everyone is following, like nowadays the ad was there, famous before the COVID. One ad was there. One sheep was a follow. One sheep takes a direction. All the sheep try to follow that sheep. Okay. So why should we, when we have all this privilege, this actually it is just a statistical tool. Okay, it doesn't. There isn't any hard and fast rule that you have to go with RSM. Okay, so you should know actually what is the requirement. What are you searching for? Okay, how good you want your search? Is it that you want to cover all the areas, or just I want to narrow it down to one area and try to search an optimal value in that area? Okay, so that is where our RSM comes in place. Yes, both we can't disagree. Each and every technique or each and every design has its or method has its own importance. Okay, so now let us see this. Yeah. So usually, in short, you're narrowing down with RSM. You're narrowing down the search. Okay. Yeah. So what is happening here is the same way. This is your current position, and you're narrowing down the search to see that you get an optimal value. So you need a sequential procedure for doing all these things. Then the objective is to lead the experimenter rapidly and efficiently along the path of improvement towards the general vicinity of optimum. Okay, of the optimum. So generally, RSM has to do this. Actually, there are many other steep slope approach and all these things to narrow it down from this area to this area. There are many statistical methods which actually narrows down. But apart from that, this optimal, RSM, what it does is it narrows down very drastically or fast at a rapid pace. Okay. So first, like this, that from first order model to you can directly go with a second order model. And you can, like we call it as a climb a hill directly or narrowing down to an optimal area. Okay, so this is the whole idea behind response surface methodology. So usually when you are very far away, this is what we call it as when you are very far away. We have some equation which is of a first order, and when you are very near, like it will go for optimum, then it is like a quadratic or a second order model. Which would be like this, something your regression equation would be looking like this. Okay, second order polynomials will be added up with this. Okay, so with this what happens is the search area will be, you can narrow down the search very rapidly. Okay, in RSM what you're doing is you're narrowing down the search very rapidly with minimum number of experiments. RSM doesn't contain most of the experiments. RSM what does is it goes with repeatability. Yes, if you're very certain that your factors and the levels are very precise, then what it will do is it will try to repeat and confirm. Actually, RSM, what does it do is it will try to repeat and confirm in this area at a very faster rate. All right, because the area is very small. So what it does, it just concentrates on some of the points that we'll be looking at. Okay, it will concentrate down just with some of the points, and it will try to narrow down the search as fast as possible. Okay. So what is happening actually? So anyhow, we have gone graphically and we have taken all the examples and that all things, but let us see something which technically we can speak. Yes, everyone knows what is this slope, right? And everyone wants to reach the target or the top of the hill. Okay, let us take this as target. Okay, so what happens is, yes, full factorial design you can do, but what happens with full factorial design is generally you will be getting a straight line. Okay, you will be getting a straight line. Okay, these are some of the levels at which I do experimentation. So when I draw a straight line kind of joining these three levels, okay, so it is actually far away black one, please consider this black one. It is still far away from the target. Yes, what I have done is, yes, I have searched this area and I know that the target is in this area. It may be this side of the hill, or it may be from this side of the hill, whatever it is. But I know the broader area of the target. Okay, so this is the broader area of the search. I am not in a restricted area of a search. I am in a broader area of a search. Yes, so the first order model won't give us won't give us an optimal target actually, or optimal response. Okay, now let us see. So the other way of doing it, yes, this way I have done, sir. You may be asking me, sir, I have done only this area. Why can't I have this way, or some levels here and some levels here? If I do this, still there is some distance. I am some distance away from the target. Maybe I am somewhere in that area or in that colony, but I didn't reach the target. That is the biggest problem when it comes with other approaches, right? Or let it be our equations even. So what is happening is, when I draw this line, there is still a gap between the search area, search domain or levels, what I am searching at, and the optimal level, what I get. So near optimal fit as a first order model lacks, so there is a lack of fit. Okay. So now if I go further, what is happening is, when I go for a second order polynomial, then I can have a curvature like this, which passes through the target or an optimal value. So now you have to decide, you need this exact optimal address or exact address, or just this thing is okay for me. If I'm going nearer to the value also, that is fine, but I don't want to spend that much of money. If I get nearer to the value, but I am searching for a larger domain and all this, yes, full factorial designs or fractional factorial designs and the Taguchis are okay with me. Okay, but no, I want to reach exactly the target, then you have to go with all these procedures. Okay, so there is a huge way, we have came a huge way of defining actually how I want to approach my target. Okay, I just want to go, I want to see, like if you see in Hyderabad or somewhere, if I climb up some big building, I can find a Birla temple. Okay, Birla temple I can see. Or if you climb up the Birla temple, I hope those who have visited Hyderabad would have visited Birla temple. So if I go with the Birla temple, I climb up the Birla temple, I can see the assembly. Okay, from there I can see Charminar also. But is that, I know that the target is there. Okay, if I say I am at Birla temple here, I am at Birla temple, and if I climb the Birla temple, yes, here I can see at a distance assembly, because it is this both are much nearer, and at a far distance I can find Golconda. Golconda Fort. At a far distance, yes, I can view this Golconda Fort. So what does that mean? My search area is assembly, or it may be the Golconda. Optimal thing is this thing, but still I am sitting down here. Okay, I know this area. Okay, so it depends on how intensely you want to survey, or how intensely you are conducting an experiment. So if you are going some medical fields or biomedical fields or chemical fields or pharmaceutical fields, exactly where I want to get these things, yes, naturally then I can go with this kind of approach, RSM. Okay, otherwise it is just a generalized survey. Like it's not only for engineers, as I told you, right? It's not only for engineers and all these things, yes, but it is for some other fields also of research where I don't require them. Yes, that is okay for me. I don't want to get exactly to the assembly building, or I don't want to get exactly to the Golconda Fort. Yes, I am fine with Birla temple. Then I can go with some other techniques. No, I want to know exactly. I want to go area, but still I want to reach assembly. Then it's something different. It is like something which Google shows you, right? When you just send your current location, starting, I don't know how many of you have done it, but when you try to send the current location to your friends, what it does is, initially it will be showing the accuracy till 100 meters. That means in 100 meters, around 5 houses will be covered up. Which house should I visit? And most of the delivery boys, food delivery boys and all these things, they come up and they call, sir, I am at the exact location, but I am not getting to it. Then I'll be saying, no, come to the 5th house from there where you're standing and all this. So then further, if you give some time to this Google map, it will narrow it down to 50 meters. Then after some time, it will narrow it down to 10 meters. So what it is doing is, this Google map itself, you can see in front of our eyes, you can see that the Google search itself, it's a very big optimization tool for us. Okay. The Google search itself is a very big optimization tool from us, from 100 meters to narrow it down to 50 meters, from 50 meters narrowing down to 5 meters, from 5 meters sometimes narrowing down to 2 to 3 meters. So that accurate search, or the search area, the area of search is going on reducing with the Google. Okay. So you should understand, like, so everywhere, actually knowingly or unknowingly, each and every one we practice this. That is what the example what I gave you with the address search. Okay, narrowing down. We are narrowing down each and every search, but yes, what we are trying to do is, we have to map that thing, and we have to understand the statistical tools, and we have to see that how good can we fit it for our condition. So it is not a big deal, actually. Yes, people think of yes, RSM, thinking of RSM and TOE. No, it is a very big headache for me and all these things. No, I strictly disagree with that. Yes, it's lack of knowledge. After lack of knowledge is lack of fit. Okay, so that is what I just generally want to convey. It is just a lack of knowledge. Lack of knowledge. What is in Telugu? There is a famous saying: if you don't know anything, we call it as Brahma Vidya. Okay, and if you know everything, and if you come to know what is it, right? If you come to like children's life, if there's something in the box, then always our mind will be jealous of opening the box and looking into what is it. Once before that, it's like Brahma Vidya. Oh, my mind is very curious of opening the box. Once the box is open, if I see that there are just stones or marbles into it, then I know, okay, let us leave it off. So then we call it as Koti Vidya, or like a monkey's game. Okay, we treat it like very casually. Okay, so this is also the same approach, and the whole idea of this STTP was to narrowing down, and like it is like keeping this thing as an open book, your mind as an open book, and you shouldn't worry about anything much, and you should narrow it down which method is very good for you. Okay, so with this, let us look into it. So before doing RSM, what you have to do is select the variable. Design variables, select the variables, and design the experiment. So once you know the variables usually. So let us take one example also after this. First, let us see your factors. You need to select the factors, and you need to select the levels. Okay, so you need to know what are the factors that are affecting the response, and you need to know the levels. Simply in RSM, I can't go for checking which is the factor significant or is the factor not significant. I can't do this in RSM. I shouldn't do this in RSM. Then the whole purpose of this RSM is a failure. Okay, so I can't do this. Okay, the whole purpose of RSM will fail with this. If I'm going to check which factor is significant, I should know the factors what I am selecting are all significant. First thing is, okay, that is where RSM is very important. So generally we don't do this. We just select some factors, we just select some levels, and we do the experiments. But yes, if you go with some literature survey, and if you do a thorough literature survey, from there you will be knowing, yes, some of the factors are significant. Like if you go with machining, speed, feed, and depth of cut are all significant terms. Yes, it is for material removal rate. The combination may change. For surface roughness, the combination may change. For material removal rate and surface roughness, yes, the combination may change, but all these three are significant terms. Okay, that is why we call them as principal factors or major parameters which affect machining. In machining, we consider these three factors. Okay, so we need to know the factors. Apart from that, we should need to know the levels. Then the duration, actual experimentation will be carried out. So here, once we do this, we carry out the actual experimentation. Then we analyze the data. So the application of regression and other techniques. So after analyzing the data, we get the regression equation, and then we use some other techniques for optimizations and all that if you want. So usually what people say is, some of the big guns in the research area, what they say is RSM itself, the regression equation, RSM itself is the most optimum thing. See, because you have already narrowed down to a particular area, isn't it? From a bigger area, larger search area, you have already narrowed down to a particular smaller area, and how much again depth you want to go there. Okay, so for generally we say this is okay. Regression equation and optimization using RSM is more than enough. But yes, if you want to do some optimization techniques and show up a big data or a big work, yes, you can use. Go for optimization techniques. Okay. So just I have taken an example of bioabsorption, and this is from a paper where bioabsorption experimentations were done. Okay. So just wanted to show you how the things happen. So you need to define output, response, and input factors. You need to define usually. Then you need to design. You need to select which one is optimal for you. That may be full factorial design or a central composite design or a box-Benkin design. Okay, so this both are again important for us. The CCD, we call it as central composite design or box-Benkin design, and we'll be going in detail of a central composite design and the types of central composite design and box-Benkin design. So yes, where this thing is there, where this can be fitted or where CCD can be fitted, we'll be looking at that. Once that thing is done, we get some regression equations. These are for main effect, these are for binary interactions, and these are for quadratic effects. So if you see the equation itself, you can say what kind of interaction. Yes, I am not I don't have a mathematical background, but yes, those who are a bit aware of that, they can, by looking itself, they can say that these are for main effects, these are for binary interactions, and these are for quadratic effects. So once you get this, you need to diagnostics, and from this, as I told you, from RSM, you'll be getting some beautiful surface plots, contour plots, and Pareto graphs, and all these things. You get it from this, and you can, after that, you can confirm. Once this thing is done, once the equation is done, actually, as I told you, these equations are fit for the region in which you are doing the search. Okay, and these equations are fit for the regions in which you are doing the search. So what I do is, instead of doing the experimentations at the levels what I have mentioned already, I will take some other levels intermediately, and what I will do is I will try to search there. I will put that value in this equations, and I will get some response from this equation. Apart from that, I will be conducting some experimentation with that levels. Actually, these levels are not included in the design, but I'll do some extra levels actually. If I say the speed was 100 and 150, or the cubic centimeter of the engine was 100 and 150, what I'll do is I'll do it at 155 and try to, because this area, search area is 100 and 150, between 100 and 150, I can use something in between also. So what I'll do is, in this area, I'll conduct some experiment. I'll try to see that the experimental, the result what I get from the response from the experimental and what I get it from the equation are equal or not. So this is called as validation of the model. Okay. So this is what we do. Yeah, this is the same procedure. So this design of experiments comes here, like selection of variables. DOE spreadsheet actually. We need to copy down the spreadsheet, okay, or the run orders, and then we need to do the experimentation. Then we need to do the mathematical modeling. Then, as I told you, we need to validate the data. So as the regression equation, what I get. So I have to validate the data, the one which I get from the model and the one which I get from the experimentation. But the levels at which I will be doing the experimentation will be different, but in the same search domain. So if these both are satisfied, then I can say that the regression equation is fit. And then I just once. Then, if required, I will go for Then, if required, I will go for optimization. Okay. So this is the whole procedure or the flow chart. Okay. Now let us go with the next. So usually type of levels, I wanted to just brief you down. When it is a 2 to the power of k levels, that is two-level factorial design. So usually two-level factorial design, we have only one thing is low and the other thing is high. So two-level factorial design is each factor is evaluated at just low setting and high setting. That is the lowest setting and the highest setting. So when you go for a three-level design, we go for a low, high, and intermediate. So a three-level factorial design is factor is evaluated at low, center, and high settings. Apart from that, I don't know how many of you heard of this. We have 5 levels also. 5 levels. So what are these 5 levels? Yes, low, center, and high is there. Okay. Then after that, what is it? Then alpha. This fourth and fifth levels. Fourth level and fifth level, we call it as alpha. So what we are doing is we are searching beyond that also. So usually when it comes to mechanical in machining, we don't try to go with fourth level and fifth level. It's very difficult for us. We can't predict it. Yes, for chemicals and pharmaceuticals and bios and all these things, you can naturally go for this alpha values. Okay, that is how I'll tell you once we get into again the next slides. I'll tell you there. Then from this search we get a second order or a second from this for 3 to the power of k also we get a second or higher order equations. Here also we get. So here we call it as this alpha, what we call it as star low. Alpha, this fourth level we call it as star low, and the fifth one we call it as star high settings. So here this is where CCD comes in place. Okay, so let us go further. So usually response surface designs are divided into 2, where you have a central composite design and a box Benkin design. A central composite design and a box Benkin design. So usually central composite design, we have uniform precision of effect estimates. At box Benkin design, almost uniform precision of effect estimates. Usually fewer runs required than CCD. Usually when you go with box Benkin, you require very few runs. Okay, very few runs. And the importance of this is also there at the same time. This is also important. But I will, my whole idea is to see that where, what is CCD and what kind of experiments can be fitted into CCD and or what can be designed can be adopted, and box Benkin also you should be aware of what is it. So the choice between these models is usually decided by the availability of the design for a given number of runs and number of factors. Note that there are other suitable designs usually available in statistical software that supports DOE. Okay, many are there, but we are only dealing with this both central composite design and box Benkin design. So usually when it comes to CCD, central composite design, let us start with central composite design. So each and every, I don't know how many of you are familiar with this design. Anyhow, in the next coming slides, this will be there. I'm trying to show you the search domain. So usually, in the previous sessions also we had this. So usually this will be my X factor with level low and level high. This is my X2 factor with level low and level high, and this will be my X3 factor with level low and level high. And this will be my search domain. Okay, just that is 3D, but I am doing with a 3D. Sorry, 2D. Okay. So one is okay. Let us go back with this. One is factorial points. What are the factorial points? They are the levels actually, the lowest level and the highest level. So they are situated at the corners. Factorial points are at the corner. Then you have center points. What does the center point mean? So if you can see how many points are there which is coming up. I'll just rewind it. Just please try to see. Yes, if it was a cube, how many points there would be? Central composite design, how many points it would be? Usually if I take a cube, how many sides it has? It has 6 sides. Okay, 6 sides. So what I'm trying to do is I'm trying to fit it on one of the faces or something. So if you can count it, it would be 6. 1, 2, 3, 4, 5, and 6 actually. Okay, 6 things are there. 6 points are there on the 6 are the central points, and then you have axial points. Okay, so what are these axial points? Why are they defined here? And why are they outside? So these axial points are called as alphas, or the star points. So CCD is often executed by adding points to an already performed 2 to the power of k design. Okay, so let us see how does it do. So the central composite design yields an uniform information of a 3 to the power of n full factorial design. Okay, then CCD contains the full factorial or fractional factorial design of a 2 level 2 to the power of n. So please concentrate here, participants. Central composite, CCD contains the full factorial fractional factorial design of 2 to the power n. Okay, 2 to the power n plus center points, which corresponds to the middle levels of the factors, middle levels. Okay, then the axial points, it is 2n, product of 2 into n. So if I say that n is 3, okay, n is 3 means 3 factors. I am searching for 3 factors. Okay, so what does it do? 2 to the power of n, n is 3, so 2 to the power of n. So I have 8 points on the 8 points here, right? 1, 2, 3, 4, 5, 6, 7, and 8 points here at the corners. Okay, 8 corners. This 8 corners of a cube represents this one. Okay, the full factorial or fractional factorial design. 8 corners. Then I have 6 center points. Okay, 6 center points. What does that mean? 6 center points of the sides. I have 6 sides, isn't it? So on this, I'll be looking for 6 center points for all the 6 sides. Okay, apart from that, the axial points, 2 to the power of n. So how many I'll be having? 2 into 3, 6 axial points. Yes, the software, if you see in the DOE, we have provision to increase this axial points from 3 to 5. I can have 4, I can have 5. Okay, so keep this in mind. But still, for CCD, keep this as mind. So what happens when I sum up this 8 plus 6 plus 6, that is the fractional factorial design or full factorial design plus the center points plus the axial points. Then totally I have 20 runs for 3 to the power of 3, 3 to the power of 3 design. I'll write it as design, 3 to the power of 3 design, then I will be having 20 runs. But if I go with this 3 to the power of 3 full factorial, I have to do 27 experiments. But here with the CCD, I am doing only 20 experiments. Okay, so this is what you need to know actually. Okay, so with full factorial design, 3 to the power of 3, I am doing 27 experiments, but with central composite design, I am reducing down with 20 experiments. So depending upon the axial points are located, the CCD can be divided into 3 types. Okay, where these axial points are located. Here the axial points are outside. If you can see, axial points are outside. But if I go here, the axial points, depending on the axial points, it can be CCC, that is circumscribed central composite, inscribed central composite, or face-centered central composite. Okay, circumscribed, inscribed, and face-centered. So generally, everyone will do mechanical and machining. They do face-centered central composite. But yes, it is like a chemical or pharmaceutical and all that. They want to go search beyond this, natural, beyond or in that area again repeatedly. So you can go with triple C or CCI, inscribed or circumscribed. Okay, so how it goes. So in CCD, there are 2 possible choices. That is number of center points and location axial point. That is what I told you, right? Center points I can go on increasing. If I want to search intensively, I can increase the center points, or the axial points also I can increase. So that is what I was explaining here, right? I can increase the center points, I can increase the axial points also if I want to do some intensive search. So how does it happen? So usually these are the factorial ones. These are the factorial. This you know, right? These are the center points and these are the star points. So we call this as star points or alpha values. So in the DOE software, we call it as alpha values. Generally, we call it as star points. So when we have combination of this, we call it as central composite design. Okay, so let us see the three things in central composite design, which one would fit for you. Okay, so this is again is an important search. I need to know which one to fit actually, or which one should I use. Okay, now coming to circumscribed central composite. So usually we have here alpha value. Okay, some additional alpha value I take alpha value. So actually my search domain was this only. So this is just an area, but this was my search domain only. Okay, I'll just hatch it up. This was my search domain area. But what I had to do is, instead of this, I want to do some experiments, or if I have some facilities, like as I told you, or feasibility, like in chemical, pharmaceuticals and all this, I have feasibilities to go beyond that area also. And somewhere in machining and all this, we don't have this feasibility to go beyond that area. Okay, if I reduce the speed of the shaft, it will become some knurling operation or thread cutting operation, isn't it? If I increase the speed beyond this particular area, what happens for me? Like you can call it the machine doesn't have capability and to take that much forces, and you may get some chatter marks. Okay, so that is a problem with mechanical. Yes, in thermal we can do this. But in design and manufacturing, it is very difficult to use circumscribed. Yes, for pharmaceuticals and chemicals and bios and everywhere, we can go beyond the search, beyond the area also. So what we did is, initially top-down approach we had, but already as I told you that RSM itself is an almost optimized area. So yes, if I want to look into something, the effect of it, I am curious of studying the effect outside also a bit. Yes, then I can use this alpha. So this design requires 5 levels of each factor. And one more thing, most important thing is, whenever you are going for RSM, okay, whenever you are going for RSM, minimum 3 factors and 3 levels are required. 3 levels is must. This -1, if you see the software, it will give you -1 and +1. But when you go with the run order, you will be having the center point. It will assume the center point directly. Okay, so select a value. Okay, select a value in such a way that when you are selecting the lower value and the upper value, select such a way that when the system takes automatically this value, like if I say 100 and 200, the lowest value 100 and 200, the system will directly take 150. So try to see that you select a value, because this is automatically, and this value is feasible for you for experimentation. Okay, so when you are selecting lower and upper value, try to see that this value, what you take lower and upper value, the center value which will come will be feasible for you to do experimentation. So this you should keep in mind. Okay, next is inscribed. So when I want to do some, okay, this sketch is not for inscribed. Circle should be inside like this. And here you will be having the search domain. Okay. Please, sorry for the inconvenience. So if I want to do intensively search inside, then I can go with then I can go with CCI, that is inscribed central composite. And here also you need 5 values, because these are the stars. Okay, these are the stars actually. Okay, or the alpha values. You can call it as stars or alpha values. Next, the most awaited or the most widely used is face-centered central composite design, or CCF. We call it a face-centered central composite design. Why we do this is, I am not interested in the alpha value here, this side or this side or this side or maybe this side or inside. I am not interested. What I am interested is this line directly, or on the face of this, on the face of the cube. Okay, I am only interested in the face of the cube. So what happens, this value I know, as I was mentioning you, right, 100, 200. So on the face only I need a value. I don't want a value which is outside this working volume. I don't want to do any experimentation which is out of the working volume. That is why we generally use for mechanical engineering, we generally use face-centered central composite design, where in the design itself you need to mention that the alpha value is 1. When the alpha value is 1, it is face-centered. Okay, so generally we require 3 levels here. Okay, generally we require 3 levels. In the before 2, we need 5 levels. Okay, in this before 2, where circumscribed is there, inscribed is there, we need 5 levels, but generally for face-centered it is 3 levels. So how we have placed this? The same thing in 3D. Factorials are the edges or corners of the cube. Then these are the stars. Okay, axial stars, or you can say this, when we add it up, it will become CCD. Okay. Once the CCD is done, now let us go with box Benkin. Yeah. So now understanding of this box Benkin is very crucial. Okay. Understanding why, I'll tell you. Many people don't prefer box Benkin. But now I wanted to tell you why generally people don't prefer box Benkin. Okay, there is a small misconception what already people say. People say that no, only at the because box Benkin considers only at the centers. Okay, the centers, it is concentrated on the centers. It is not concentrated on the corners. Okay, it is not concentrated on the corner. It is concentrated on the centers. So, excuse me, it is just concentrated on the corners. Okay, this is what this is what people try to assume. Okay, yeah. So this is what actually people try to assume. So whenever you are doing an experimentation or whenever you are considering the box Benkin design, what we say is, we say that we concentrate on the midpoints. Yes, no doubt the statement is right. In this design, the treatment conditions are at the midpoints of edges of the process space and at the center. Okay, no doubt this thing is right. These designs are rotatable and require 3 levels of each factor. Okay, so these designs that consist of combinations of 2 to the power, yes, the same like these things. What are the properties of? Yes, they are efficient, they are rotatable, no corner points on hypercube. They are saying this no corner points on hypercube, but this is actually the misconception. Yes, there are there on the corners. Yes, we have the things on the corners. Yes, we are considering on the corners, but what is happening? That is what is the twist here. So what is it doing is, box Benkin developed a 3-level incomplete, in 1960, it developed a 3-level incomplete factorial design as an alternate to labor extensive full factorial design. Okay, it is just an alternate. Yes, CCD is also an alternate for FFD, and box Benkin is also an alternate for FFD, that is full factorial design. But what is happening in this? Experimental matrix are built by means of 2-level factorial design, that is -1 and +1, with incomplete block designs. So this is a statistical thing. We can't define exactly how, as we have defined CCD, isn't it? The number of runs what we get from CCD, we could have defined it, but here we can't define it. So the final matrix is completed with several replications of central points. What improves precision? So what is happening here? Please concentrate on the sentence. The final matrix is completed. That is the run order, what the chart what we get, right? With using which we do the experimentation. So when we come with this final matrix, what it is saying is, with several replications of center points. Yes, no doubt, as we were defining in the first, we are concentrating on the center points or the midpoints. So here also it is done doing. So here also what we do is, here we take run order, or we produce the run order in such a way that we get many replications at the center point for each and every factor. For each and every factor, there are these replications. Okay, there are these replications. So we are maximum concentrating on the center point. So what does this mean? So what does this mean? There is a need to understand when can you use box Benkin design. Okay, there is a need to understand each and every time if I say CCD is good or box Benkin is good. No, that isn't the case. You need to know why we need replications, several replications at the center points. Okay, this is the most important aspect. When you will try to conduct this kind of experiments, you should ask yourselves. You can conduct this kind of experiments when you know the optimal levels already. Okay, you know that the levels what I am doing, the center point what I am doing is just an optimal value. Okay, you know that it is an optimal value. Okay, you don't need to do anything else. I know that it is an optimal value. Yes, I know that it's an optimal value, but out of curiosity what I do is, okay, so if I'll write it down like for the mileage example, okay, number of, or you can like it speed, feed and depth of cut. I'll take this for this example. It was like 90, 120, 150 velocity, okay, meters per minute. Feed was 0.1, 0.2, 0.3. This one was 0.1, 0.2, 0.3. So I had done already experimentation or from previous studies or from the initial trial or pilot experiments. I know that this combination is giving the right results for me. Okay, this combination is giving the right results for me. Now, why should I? So I know that I have an experience, or from my previous experience, I know that this is giving the optimal. This is the optimal levels for me for getting the response. But still, I have a curiosity. Okay, still I have a curiosity. So what I do is at present, still as I have a curiosity, right? Researchers should have curiosity of the search domains. Okay, so now I have a curiosity, and what I do is I try to go and search in these areas again or at different levels. So now what happens? Let us go back. Now, anyhow, I have this curiosity, right? 120 is there. Okay, 120s are there, then feed is there, and speed is there. I know that these are the optimal values, but I have a curiosity. So what I do is I try to search at the corners also. Okay, I try to search at the corners also. That is why when you look into the design, okay, when you obtain a design and you keep a central composite design one side and box Benkin design on the other side, you will try to see that there are many replications at the center point in box Benkin, but there aren't many replications in the CCD, that is central composite design. That is one way of looking into it. Now, there is no experimental point in the design where all factors have extreme values. So this is one thing you have to keep in mind. Okay. So here what I did is, yes, I have gone through the search here. Okay, and I am trying to search area. But in that combination, anyhow, when I'll be showing the run orders, they will be knowing this. But what I do is, I don't go for extreme conditions here. Okay, all high. That is, what is the all high condition here? 150, 0.3 and 0.3. This combination, I will not conduct experimentation in box Benkin design. Is it okay for you? You have to decide. As a researcher, you have to decide that extreme conditions, box Benkin design will not, you don't have levels at which you will conduct or run orders which will conduct at extreme conditions. This I'll show you. So is this okay for you? Yes, in CCD, central composite design, you can conduct for extreme conditions. But in box Benkin design, you can't conduct experiments at extreme conditions, because you know that there are worst conditions and the design or the experiment may fail. So this feature might be beneficial in experiments where undesired phenomena might occur in extreme conditions. So usually where you are expecting that there is undesired phenomena will occur at the extreme conditions, there this box Benkin design will try to avoid the extreme conditions. So that is why we don't conduct at extreme conditions in box Benkin design. This feature might be beneficial experiment where undesired phenomena. So again, sorry for I have repeated this sentence. So the box Benkin design has only two significant restrictions. What are the two significant restrictions? The number of experimental factors has to be equal or higher than 3. Okay, and the box Benkin design should not be used for fitting other equations than second order polynomial. So these are the two restrictions which are there with box Benkin. Apart from that, they don't conduct at extreme levels, and apart from that, you should be knowing the optimal levels, and you are just searching for and just additional solution. That is where only box Benkin design fits. So this design requires fewer treatment combinations than central composite design. So the number of experiments, as we are already narrowing down the search. Actually, I have already the optimal condition, but just I'm trying to search an area beyond the optimal condition. Then only I can use box Benkin. So the number of experiments required here are fewer than the central composite design. Okay, in cases involving 3 to 4 factors. So box Benkin design is rotatable, but it contains regions of poor predictions quality like the CCI, because these are inscribed. Okay, so poor things are there. The missing corners may be useful when the experimenter should avoid combined factor extremely. So that is what in the previous slide also I told you, extreme conditions are avoided. So this property prevents a potential loss of data in those cases, and this requires only 3 levels for each factor. So box Benkin design is similar to like inscribed, sorry, not inscribed, face-centered one. So this is what is happening. So let us go with this. So most everyone is familiar with this schematic diagram. So the full factorial design is the complete area search, left and right. Okay, left and right. If I say that of Hyderabad, yes, left and right of Hyderabad, you are searching. So the most foolproof. So you can't be fooled when you do, because as you have done the complete search, you can't be fooled. So it is foolproof. Sometimes here you may be fooled with some of the other data, but full factorial design you may not be fooled. But also the most labor-intensive design. Okay, full factorial design is the most labor-intensive design. But as I told you, depending on the requirement, you can go for full factorial or CCD or box Benkin design. But yes, all of them, experimentation in any one of this, depending on the requirement, you try to select a full factorial design or box Benkin design or central composite design. Simply don't force fit. We just call it as I just generally call it as force fit. Don't force fit your design into any one of this. Okay, it's a very bad practice, because because you are taking so much of effort of designing this and doing experimentation, all that. But if you force fit the design, you won't get optimal values. It is just for namesake you are doing the experimentation, or for just for like a documentation, I will call it as. So don't force fit it. So unrestricted number of factors and unrestricted number of levels. You don't have any restrictions here. So you can go with any number of factors, any number of levels. Now let us go for CCD. So I already told you how the calculations is there and what are the factorial points, center points and axial points. Already I have defined you here. So factorial points are usually so and so, and alpha is number 1. Alpha is 1 when it is face-centered one. So generally we go for 5 to 3 factors only. I don't go for more than that here. Sorry, levels. Okay, factor levels 5 to 3, 3 to 5 we go. Box Benkin, I have told you what are the restrictions with box Benkin. We are only concentrating on the middle levels. For most of the time, I am concentrating on the middle levels. That also I will tell you why it is there. And we don't go for extreme conditions. So what happens is, a design specifically for second order polynomial, that is fine. Minimum 3 factors are required. Contains region of poor prediction quality. Sometimes we are only trying to check outside of the scope a bit. So that is why box Benkin is there. Yeah, so this already we have seen in detail of central composite and box Benkin of this. So now let us go with the run orders, how it is. Okay, I will compare the let us anyhow. If you see central composite face centered, -1, +1, and we'll be having some zeros here. Okay, these are the center points actually. Center points when alpha is equal to 1. So circumscribed alpha will be equal to -1.682, and it is CCI. Okay, CCI, this is CCC or CCI. Then these values will, alpha values will be something like this. So this actually are called as coded ones. So +1, -1, or some values, they are called as coded ones. So let us go with box Benkin now. As I was telling you, box Benkin for each and every layer, the replications of the center point. See, if you see here, no other design has this many replications. Here it is a replication here. Okay, for factor 3. Here there are replications for factor 2, and here there are replications for factor 1. So we are going with the replications of the center points here for most of them. And the number of runs, if I see, are 3. Center points, if I this was for 3 center points. If I increase in software, we have this provision in for box Benkin. If I increase the center points for 4, someday the run order will be 17. If I increase the center points for 5, the run order will be equivalent to CCD and CCF. Okay, so usually if I see, generally if I go for 3 center points, then we have only 15 runs I need to do, but here I need to do 20 runs. You can assume from 27 run orders, I narrowed down to, with a CC central composite design is 20, and for box Benkin it is 15. Okay, so around 27 minus 15 is around 12 experiments I need to do less. Okay, so you can assume how good it is. Okay, then just wanted to compare here face centered with some realistic values. So in realistic values also, if you can see, the center points are repeated here. Okay, so I hope each and every participant is now aware of actually which okay, so which design has to be selected and what is the condition for that. Okay, you can take CCD, you can take box Benkin, you can take full factorial design. Okay, so for the selection of things. So now let us see the number of factors of 2 with compared to central composite and box Benkin. So if it is a 2-factor one, then you have 13 runs. You have 13 runs. Yes, levels will be 3. I am not speaking about levels. Levels are fixed. It is a 3 level. So usually RSM deals with 3 levels. At any cost, you have to go with 3 levels, or it will take directly. So you don't have a box Benkin design for this. For 2 factors, they don't have box Benkin design. Yes, for 3 factors, we have 20, and here we have 15 runs. For 4 factors, 30 runs, and here 27. See, the gap is reducing here. If you can see, the more number of runs, the gap is reducing, and it is going vice versa. For 4 factors, this is 33 or full 52, and this is 46. Okay, so again the gap is reducing, and for 6 factors, if I say, almost it is same. Okay, so you can assume now where you can fit your experimentation. Okay, you want to go with any of the experimental design. So preparation for RSM. Preparation for RSM. So what should you do is, what response variables are to be measured, you should know how they will be measured and what sequence they will be measured. So the run orders you should know. What factors are most important and therefore will be included in the experiment. So you need to know some preliminary or pilot studies you should know for selecting the factors, and which are least important, you can just vomit it down. And can this factor be omitted? Yes, then you can vomit it down. What extraneous or disturbing factors must be controlled, or at least have their effects minimized. So if you have some factors, yes, you can do that. What is the experimental units? You should know. What is to say, what is the piece of experimentation material from which a response value is to be measured? What are the experimental units and replications? All these things should be kept in mind. The choice of factors and level determine the size, type, size, and experimental region. How the search area, how narrowly you have done it or how broadly you want to do it, it depends on the selection of the factors and the levels. Okay, so the same one, the mileage example, what we have taken it, right? We had 2 examples where I had an 100cc Splendor and 150 cc pulsar. Okay, 150 cc pulsar. And the same thing what I did is I kept the same data into one is the CCD, central composite design with the face centered, and the other one is box Benkin design. So if you see, as I told you, we did it for 2 levels only, isn't it? We did this experimentations for only 2 levels. What were the 2 levels? Let me write it down here. Just 1 second, guys, please. Hello? हाँ संजय जी, गेट पे एक बार दीजिए. नमस्ते, प्लॉट नंबर 93 को पंपिंचे साइन करके. Okay. Yeah, sorry for the disturbances. Yeah. So what I did is number of persons were 1 and 2. CC of engine was 100 and 150, and average mileage was not mileage, average speed was 50 and 70. So these were the levels. I had 3 factors, but I had 2 levels. So what this design has done is, if you see the number of persons, it has taken some middle. From where should I bring 1.5 person? Yes, technically speaking, if I say that a person is of 70 kilos, yes, a kid of 35 kilos, I can accommodate there. Yes, if you are able to do that with your experimentation, yes, naturally you can go with RSM. Okay, then yes, 150 cc. Yes, 150 cc bikes are available in the market. Okay, yes, so for that, yeah, I can accommodate here. And the average speed is 60. In between they have taken, yes. As average speed 60, I could maintain. That shouldn't be a problem. Yes, you can accommodate this kind of changes, this kind of levels in your design or experimentation. Yes, naturally you can go with this. But how many runs are there? 20 runs are there here. Okay. Now let us go with box Benkin. What it is doing? It will be not as similar to the design what I showed you, because this is the design which is generated from the DOE. Yes, here also the middle levels are taken. That is 1.5%, 125 is the CC, and 60 is the average speed. So if my optimal area is 150 and 125 and 60, if this is the optimal one, yes, if I want to conduct a study and do a regress one, then I can go with this kind of box Benkin design. Okay. Yeah, before ending up this session, I would like to give you a glance about a small experimental setup and the design. Everyone knows this is a wire cut EDM or wire cut EDM machining, and some of the variables are like this. We have taken 4 variables: pulse on, pulse off, peak current, and servo voltage, and a 3-level experimentation design was selected. Just I wanted to show you how the graphs and things will be there. So actually it was done for multi-objective optimization. Actually, multi-objective optimization, this thing was done. So we had 4 factors, 1, 2, 3, and 4, and 3 responses, 1, 2, and 3 responses. That is material removal rate, surface roughness, and curve. Okay, and with this the design was conducted, and for that we had around 26 experiments came up through the design, and this was the workpiece where we had the cuts. Okay, so here they call it as like, these are factorial, these are axial, and these are some center points. Okay, they are taken some center points and they are conducted, and these are the ANOVA results for material removal rate. And what we can say is the maximum concentration was the C factor on the material removal rate. What is the C factor? Current input. Current input. When the current input is more, the what they call it as the material removal rate is more. And they are conducted the experiments with R square and adjusted R square, where Salop sir yesterday he gave a wonderful mathematician from IIT Kanpur, and he gave a very good thing. So I don't want to get this. And Dinesh from IIT Palakkad also was with ANOVA. So if I interfere in this, it would be like one of the things. So you can understand this. So with this, you know the contribution of this. Okay, and you know the values of p values. It is less than it should be less than 0.1. If it is less than 0.1, then only it is significant. Okay, so most of this are not, these interactions are also there which are not significant. This is not significant, this is not significant. Okay, these are some of the things which are not significant, so you can omit that. Okay, you shouldn't consider that. So next time when we do the experimentation, when we select the interactions, when we select the interactions, right, for the thing, there what I will do is I will neglect this. I will only select the one which are good at. So I will be only selecting this. So this will be only included in the regression equation. Okay, so this interaction will be only included in the regression equation. So once I have done this, once I know the optimal values, what I do is, these are not the optimal values. So what I do is, I'll deselect this. Once again, I'll go back in the interactions, I'll deselect these ones which are not optimal, because these are these F values are greater. So I deselect this. When I deselect this, the regression, in the regression equation, these interactions will not be there. Okay, so that I can do it. Now for surface roughness, if I see the input current is the most affecting problem. This is a current input power is the most affecting thing. So here the experimentations were conducted good. Generally, when you do the experiment, there are very least chances that there is a huge variation of more than 0.2 between the R square and the adjacent R square. Because if you have done the experimentation properly, 99%, 99.99%, okay, I can't give more than that. So 90%, you can get this value, this both value, R square and adjacent R square value, between the difference would be less than 0.2. Curve also, what it is saying is this one and this one, both are affecting actually. Both the parameters are affecting much. And here also, this one also the second parameter which was affecting. Okay, servo voltage actually, that is servo voltage. Okay, for surface roughness and curve also, this was happening. So what happens now comes the beautiful part of it. So why you need a surface actually? Okay, what is that you are getting from this surface is the most important thing. So when you are going for an industry or something, depending on the requirement, when I have this kind of graphs or setups, so depending on the requirement, no, for me in the surface finish and all this is not important. I need only material removal rate. So I want to search for only maximum material removal rate and all that. Then from this graph, if I search this point, right, this is the peak. Okay, my pen is also red now. So if this is the peak, I'll only select the levels which will give me this peak. No, I want to concentrate only the surface roughness or a surface finish. Okay, so what I'll do is, then I'll be selecting somewhere where this material removal rate is less. Or if I go to the next graph, I'll select a point where the surface finish is good for me. And at the same time, the material removal rate is good. If I go back, the material removal rate was increasing like this, right? With T on and input voltage. This is for, first one was for input voltage and servo voltage. Second one is T on and input voltage. So depending on this, depending on the requirement, what I do is I'll be going on selecting. So this surface will aid me for selecting the required levels of input current. Major advantage of RSM lies here. It is not just a beautiful graph which is there. It is the feasibility of the levels and selection of the levels depending on the requirement. So once I have searched this domain and all this data I am having, now the industry, if you say that I am a manufacturing industry, or I am a small scale industry in Balnagar, and if I say that this is the area what I am looking at, okay, so there I have already searched all this area. So depending on the requirement, the engineer who is available can select any of these points from the graphs, and he can go and give that parameters as input to the machine so that he can do all these things. So this is for curves. 1 second. हाँ संजय जी, अरे 5th में लास्ट का जो व्हाइट कलर गाड़ी है ना, कार है, बस वही पे अंदर आ जाइए अंदर। अरे अरे यार, एक्चुअली वो क्लास में मीटिंग में हूँ मैं, 5 मिनट दीजिए मेरे को। Yeah, dear participants, so this is the importance of this curvatures actually, this beautiful curvatures what I get. So engineer, when you give this data to an engineer or a researcher, directly looking at the data, I know what parameters or what levels should I go with for getting a particular kind of a response. Okay, so this is the beauty of RSM. So now, with this, I would like to end up this session. If there are any queries that you would like to communicate, or you would like to just discuss, I would open this session for discussion actually. I hope Varun sir is there. And,
yes, sir. Yes, sir.
Yeah, Varun sir. So I hope I have given the in and inside out of the experimentations, and I hope that every participant is satisfied, because this is my last session for this STTP, and I hope I have satisfied all the participants and given them an overview how actually this thing is. So I hand over the session to the coordinator of this STTP, and the session is open for any queries. So if anyone is having any query, please.
Yes, so dear participants, if you need to get any clarification, or if you have any doubts, please you may ask any doubts. So I hope RSM, the concepts of RSM are clear, and you have at least understood when and where we are supposed to use RSM. And sir has given very good examples, with starting with very easy to understand case study, starting with address how we are able to navigate. And this actually is even the case when we try to optimize any problem statement. So this is how it is also done. So the steepest descent type of problem statements or optimization problems are all working on the same principle. So that's what actually is being done by Dr. Sandeep sir. So if you have any doubts, it's fine. Otherwise, we'll end the session, and we'll have an afternoon session at 1:30.